Hello viewers, this question again is from A-level physics and the chapter is thermal physics. This is a past paper question and the paper is 9702/41/May-June/23, question number 4. And the question is asking you to state two of the basic assumptions of the kinetic theory of gases, and you will score 2 marks for this. This is part A of the question. I have written 5 assumptions that are there. You can select any of the 2 to write in the answer. So the assumptions are that assumption number 1 is that gases consist of large number of particles, tiny particles, which are identical to each other. Particles can also be called molecules here. Number 2 is collisions between the gas molecules are elastic collision during their random motion. Time of collision is negligible compared to time between collisions of 2 particles or interval between collision of 2 particles. Now this is like if there are 2 particles moving randomly in a container and they strike with each other at this particular moment, they are going to go away from each other or divert their parts from each other, and the time that they come and collide with each other again is going to be a long interval. So the collision is hardly for, call it for millisecond or microsecond, and the interval between this collision and the next collision could be, let's say, 5 minutes. So the comparison of 1 millisecond and 5 minutes is a big comparison. So this is what this point means. Then volume of gas particles is very small compared to volume of container. Say you have a container like a Pepsi bottle with you, and this is an empty Pepsi bottle, means there will be air inside. If the air is compressed, the particles of the air are going to take a very small volume, whereas compared to the volume of the bottle, the comparison is huge, and we can say that the volume of gas particles themselves is very small compared to the volume of the container, that is the Pepsi bottle. Forces between particles are negligible except when they collide, because the distances between the gas particles is large, so the forces between them, definitely forces are the gravitational force of attraction. So gravity itself is very weak force, and then the distance is large compared to the size of the particles, so the forces can be taken as negligible or no forces between them, only except when they collide with each other. So these 5, and there is another one, I have not written it here. We could include that in these one of the 5 here, and that is that the average kinetic energy of the gas particles is directly proportional to absolute temperature of the gas. Now out of these you can write any 2 and get 2 marks. Then we go to question. I'm sharing the question PDF with you, So we go to part B of the question in which there is a gas X in a container which has a pressure 2P, volume V, and let's assume that the temperature is T. This gas is taken to stage Y at constant volume, then to stage Z at constant pressure, and then to stage X again at constant temperature. So we know that PV is proportional to T, or PV over T is proportional to a constant. So using this equation and this X, we can make an equation. PV is equal to nRT, where N is number of moles and R is molar gas constant. In place of P, I write down Px, then Vx is equal to nRTx, because he is asking T in terms of P and V. So making Tx as subject of the formula, we get Tx equal to 2PV over nR, and this is the answer, so we write down the answer and get 2 out of 2 marks. Part 2 of part B is asking you to sketch a graph of P and 2V, taking P to be on y-axis and V to be on x-axis, and then the position of x position of the gas is marked for you in the question. So x is 2P and V, so we have a point x here. This is the point x. And then just look at this, x is 2P and V. And then at constant volume, we go to y, where P is P and V is V, constant volume. So the line, the point that we get for y is over here. And then going to x, going to Z, the pressure is P and volume is 2V. So we go from P to volume 2V and get Z here. When this is done, there will be straight lines for constant volume and constant pressure. That means this line is going to be here like this, and this line is going to be like this. But when we go from Z to X, from Z to X, it is inverse proportion. So it is going to be a curve having maximum gradient at X like this, and minimum gradient at Z. Why? Because the pressure is maximum at X. So pressure is increasing from Z to X, from P to 2P, and with inverse relation. So it is going to be a curve. So we get 3 out of 3 for this part of the question. And then we go to next part of the question. Part P, the pressure, V, the volume, U, the internal energy, and W, the work done. First law of thermodynamics tells us that heat or quantity of heat energy supplied appears as change in the internal energy plus the work done. Now if heat is supplied, it will be plus. If internal energy increases, it will be plus. If work done is on the system, it will be plus. Otherwise, there will be minus. Keeping in mind the situation given in the question. Coming on to x to y change, if we look at the change, it was x to y, constant volume, the temperature had reduced. So when we talk about x to y, the thermal energy transfer to the gas would be minus U, and increase in internal energy will also be minus U or minus delta U, because internal energy actually depends on the temperature of the gas. In x to y, temperature has reduced to half, so it has reduced, it will be minus. Whereas there is no change in the volume, so work done on gas is 0. In y to z, the volume has increased from V to 2V. That means that work has been done by the system on the environment, so we'll write down minus W here. This can also be written, minus W can also be written as minus P and V. This in y to z, when we look from here to here, temperature has increased from T/2 to T because heat has been supplied. So when thermal energy has been provided to the system, we will write plus PV here, and due to this heat supplied, the internal energy of the system will also increase, because the kinetic energy of particles due to increased temperature will also be increasing. So we will write down the internal energy increase as plus U. So in this case, the thermal energy transfer to the gas in total will be plus U, that is increase in internal energy, plus the heat energy itself. Now we discuss the last row, that is Z to X, and go back to this page which explains the changes from Z to X. The volume in Z was 2V and the volume in X is V. That means the system has been compressed. That means the environment has done work on the system. So it should be a plus W for the work done, which has already been given to us by the question. But at the same time, the temperature remained constant. We know that when gas is compressed, it heats up, but the temperature remained constant. That means that the compression was a slow process, and the amount of heat produced during compression has been given out to the environment, so temperature remains constant. That means heat has been lost by the system. So we are going to write minus W in the thermal energy transferred to the system. Now there is no heat supplied to the system, so increase in internal energy will be 0, and this is how we complete our table in part 3 of the question, and whole question is completed. Please like and subscribe to my channel. Thank you very much.